Okay, so let us start the video by recalling that in the previous video we were calculating average speeds of a falling rock which was released from a 150 feet cliff over some given intervals of time, and we in fact also calculated the speed at a given instant of time, which we called the instantaneous speed of the rock at that instant of time. Now one can do this for a general function also, and that gives rise to these average rates of change. So today we are going to see how these average rates can be defined similarly like what we did for average speeds, or how we calculated average speeds. It's exactly similar to that but for a general function, and how these rates are related to these geometric objects called secant lines. I think if I am remembering correctly, in the previous video also we discussed a little bit about how average speeds are related to secant lines. So let us start. Average rates of change and secant lines. If a function y equal to f of x is given, then we calculate the average rate of change of the dependent variable y, or the output y, with respect to the independent variable x, or the input x, over an interval say x1 comma x2, which of course has to be a subset of the domain of the function, as follows. In our average speed case, we were calculating the average rate of distance traveled with respect to time. In this case, we have general y which depends on x. Previously, we had distance depending on time, and the formula is of course this: change in the y value divided by the change in the x value as x varies from x1 to x2, that means in this interval, which is just simply this: f of x2 minus f of x1 divided by x2 minus x1. Now if we give this x2 minus x1 some name, say h, then x2 becomes x1 plus h, and the denominator becomes h, where we can write where h is x2 minus x1, and which just simply means that h is the length of this interval x2 minus x1. Where h is defined to be equal to x2 minus x1 is the length of this interval. Just like while calculating the average speed of the falling rock, we divided by the length of the time interval, in this case general input interval. Now, how is this quantity related to secant lines? So, the geometric situation here is of course this. Because we have taken a general function, we don't really know what its graph will be. Its graph will be something, some curve, say something like this. So, this is the graph of y equal to f of x. Now, the point that corresponds to the input x1 on this curve is this. So, this is the point x1 and this is the point on the graph corresponding to x1. This is P and its coordinates are of course x1 comma f of x1, and the adjacent point, which is x1 plus h or x2, same thing, is say lying here. x2 will lie to the right of x1 of course, because that's how we have chosen the closed interval. So, say this is the point Q and its coordinates are x2 comma f of x2, which if you want to express in terms of x1, you can write x1 plus h comma f of x1 plus h. So, you can now see that the average rate that we have calculated here is the difference between the y coordinates, that is, this is f of x1, right, on the y axis, this is f of x1, and on the y axis this is f of x2. This is the y axis, this is the x axis, this is the origin. So, f of x2 minus f of x1. So, this much is our delta y, whereas x2 minus x1, that means this much is delta x. Now, if we join these 2 points P and Q by a straight line, or if we rather consider the straight line that passes through these 2 points, then we end up having a right angled triangle. If you want to give this point a name, say we call it R, then we get the right angled triangle PQR. Now, in this right angled triangle PQR, what is delta y divided by delta x? This is just simply, if we just express things in terms of x and y coordinates, then this is y2 minus y1 divided by x2 minus x1, and y2 is of course f of x2 and y1 is f of x1. That's how we are understanding these quantities. Then from the formula for the slope of a straight line passing through 2 points, we see that this is nothing but the slope of this line, and such a line which joins which passes through 2 points on a given curve is called a secant line to the curve. So, it turns out that the average rate of change of y with respect to x is the slope of the secant line drawn through these 2 points which have arisen from the interval x1 comma x2 over which we are calculating the average rate of change of y with respect to x. So, this is the relationship between secant lines and average rates of change. Average rates of change turn out to be equal to slopes of secant lines related in this way. And a general definition of secant lines is also given, but it is just simply that if a curve is given in the coordinate plane, you have 2 points on the curve, you join them by a straight line, such a line is called a secant line to the curve. Okay, now we come to the second example in the sense that, you see, we said previously that we are going to see two examples of rates of change, two types of rates of change. One of them is the rate of change of distance with respect to time, which turned out to be average velocity and average speed, and which gave rise to instantaneous speed or just speed at a given instant of time. But now in this second type of example, we are going to see population growth. So this is example 3 actually, and this figure is for that example only. So example 3 involves the population growth of fruit flies or Drosophilus. You see that if you keep some fruit, if you leave it in the open, after some time, some very small flies will be flying around it. So those are Drosophilus, extremely small. So it's about their population. And but before this example starts, the author also says experimental biologists often want to know the rates at which some population is growing under controlled laboratory experiments, controlled laboratory conditions, because that's how they are going to study what is going on in the population. Or say, for example, you have in a controlled laboratory condition in a given situation that the biologists have set up, maybe they will release two different species. One of them eats the other. Then they will see how the two populations change, okay, how the numbers change, and this idea or this thing gives rise to some differential equations also. We will see later. They are called evolution equation. So something similar is happening, but here we have only fruit flies. So the example starts like this: the average growth rate of a laboratory population. That's sort of the heading for this example, and then what is actually written in the example is this. The above figure, we can say the adjacent figure, shows how a population of fruit flies grew in a 50-day experiment. The number of flies was counted at regular intervals. And these points, some points were plotted. The counted values were plotted with respect to time, because these are the numbers of flies. This is the time. Counted values plotted with respect to time, and those points were joined, and the points joined by a smooth curve. Well, it does not look really smooth, but you understand. In the text it's given nicely. And the points are joined by a smooth curve. Find the average growth rate from day 23 to day 45. Okay, so this is the problem. So that means we have to look at the figure, because it's only from the figure that we will know what was the population count at some given instant of time. Note that unlike the rock falling example, where we had a formula, a precise well, I should not say precise, but some formula was given that the distance that the rock fell in time t is t seconds is 16 t square feet. Some sort of formula is there. Here, however, it's given as a plot, and this is more realistic, because in realistic situations, when you perform some experiment and when you record your values, then that's what you get first of all. Then from such plots, what you do, you first of all find average rates, like how we have been asked to find here. Then from those average rates, you calculate several such average rates, and then you find the instantaneous rate at some given instant by using the limiting procedure that we discussed about in the rock falling example also. Then when one calculates such slopes or instantaneous rates, you may come up with some sort of relationship or equation involving several such rates. These type of equations are called differential equations. Once they are solved, then only you get a formula for the curve, and hence then you know what is going on at what instant of time. So that is the usual procedure. So anyway, now here we have to see what is the average rate of at which the population is. It's of course increasing, but differently at different instants of time or in different intervals of time. For example, when the population started increasing, then it increased slowly, increased slowly. Okay, that means at a slow rate, but then suddenly it picked up. The rate became much more than say this interval. Then it reached some maximum rate, and then the rate started to fall, and the population, should I say, got stabilized at this level. It kept on increasing. It did not decrease, but still it increased at different rates. Okay, so now what happens is this: day 23 lies here somewhere. From the figure it does not look like that, because I am saying that this is 23, whereas it is very close to 25. I mean, you should understand that this, the way I have drawn this, it is not meant to be geometrically accurate. But you can understand that, say, this is 23, here we have somewhere 24 and then 25. So this point is our, we can call it P. I do not want to make it extremely cluttered. This point is P and its coordinates are 23, 150. And when you look at day 45, that means this one, then the population reached this stage, and which is the point Q. This I can of course write here. Its coordinates are 45 and 340. 10 less than the maximum population that we have here, 350. Okay, so what we are now doing is that we are going to join these 2 points. So this line is a secant line to this curve, joining these 2 points P and Q. And the difference in the population in this interval, that is this 23, 45, this interval, in this interval the population increased from 150 to 340, and the difference in population, P represents population or the number of flies, the same thing, is 190. The difference is 190, and the difference in the days is 45 minus 23, which is 22. So the average rate will be what? Delta P divided by delta T, and that average rate turns out to be approximately this. You can roughly understand what happened biologically around this point, and why is the population increasing at a higher and higher rate. That's because when things started, or when the experiment started, there were not it will not be zero of course, but say when you started the experiment, in your day 0 you just released some flies yourself, but then there is some sort of food source, some fruit is also there in that experiment. So the flies started to reproduce, then there were more flies, and then they reproduced more. So that is why the rate started increasing. But then after some stage there were many flies, and then there was competition in reproduction. The food also started to diminish, So that's why the population started to, I should not say go down, but the rate started to go down. Then after some time, if there is no, if the food source is not replenished with some new fruit or something like that, then it will start going down. So roughly that must have happened. Okay, so here the solution is just simply this. The average rate of increase of the population in the time interval day 23 to day 45 is that is 190 divided by 22, and that is approximately equal to 8.6 flies per day. So approximately 8.6 flies were being burned per day. That is the rate in this time interval. And then in example 4, we have been asked to find the rate on day 23 itself. So that is going to be the instantaneous rate. So just like how we calculated the average, I should not say average speed, but speed at the instant 1 second of the falling rock. Do you recall how we calculated that? We made the interval, that instant of time, which is the 1 second mark, we kept that constant, and then we made the interval smaller and smaller by considering, raising the other boundary point and making it come towards that 1 second mark, and then calculating average speeds over those shorter and shorter intervals. And then we saw what happened to those average speed values. We found that they were getting closer and closer to some value, and that some value we defined to be that speed of the falling rock at that 1 second mark. So here also we are going to do something similar. So let's first write the statement of example 4. Just a moment. How fast was the number of flies in the population of example 3 growing on day 23 itself? How fast was the number of flies in the population of example 3 growing on day 23 itself. Okay, So now we are going to calculate average rates over smaller and smaller intervals, shorter and shorter intervals, keeping this day 23 boundary fixed and moving this right hand boundary closer and closer to this left boundary. And the intervals that have been chosen and the corresponding average rates are given in the text like this. So here I will just simply write the solution briefly just to show the essential thing. So our P point is going to stay fixed and the Q point will change. Say we have that Q itself, that is 45, 350. In this case, the average rate is of course 350 minus 150 divided by 45 minus 23, which turned out to be equal to approximately 8.6. But then we choose a closer Q than that one, and that Q is 40, 330. And keep in mind that these are actual points on this graph. So when say this is 40, then this is 330. That means 10 less than that population, 340. In this case, the average rate is 330 minus 150 divided by 40 minus 23, and this turns out to be approximately equal to how much? 10.6. We understand because we are coming from that side. No, there we had a pretty low rate, but then it will increase because the slope of this line will be getting more because the line is getting steeper and steeper. Now if you look at this point now, let me just take the risk of drawing a little bit more in this figure itself. So if we are here, then our new Q is this. So if you join the previous P and this new Q, you are then getting this line. So now the average rate value will be equal to the slope of this second line, because this line is steeper than that one, the previous one. So the value will be more. Previously it was 8.6, now it's 10.6, approximately 10.6 twice per day. But then there are other Q values also. I think one more or two more values have been taken. An even closer Q than this is 30, 265. minus 150 divided by 30 minus 23, and this is approximately equal to 13.3. Well, so it jumped from 8 to 10 and then 13 because it's getting steeper and steeper. And then there is one more, which is oh, I think I missed one. Okay, that's why it oh wait, I think I made a mistake. This is not 310. Yeah, I mixed things up. Sorry for that. I mean, this is not 265, it's 310. So that's what happens when we just simply have to copy. And the point here is also, I mean, the day mark is not 30, it's 35. And then the next one is that, comma, 265. And for this point, the average rate is 16.4. Now if one does this not just for these 4 values but several more values, somehow getting the actual figure, I mean the actual graph that is given in the text, and one does this, then one eventually will see that these secant lines are approaching the tangent to this curve at this point, which turns out to be roughly this line. Yeah, in this figure it looks awful, but you can understand that this is the tangent. In the actual figure that's given in the text, this will be the tangent line to this graph at this point P23, 150. Now this tangent line happens to pass through these 2 points. One of them is B35, 350, and this point, which is, where should I write this? Let me write it here. A, its coordinates are 14, 0. That means this is A, that one is B, because as you make your Q closer and closer to 23, the point keeps moving towards P, the Q point keeps moving towards P while always being on the curve, and correspondingly the secant line also moves like this, and in the limiting case it will coincide with the tangent. So that is why the slopes that you are getting for this new positions of the secant line, they will approach the slope of the tangent. So we just have to calculate the slope of this line that joins A and B, and that slope has this value. Did you see how fast the ruler fell? So in reality it's quite fast, and that is why the distance that the rock falls in t seconds is 16 t square feet, which is in fact for a given t this is quite high. That is believable. Okay, so whatever I just said I did not again write. So the thing here is that the slope of the line, I mean I do not want to write that part where we are going to write that these values are approaching the slope of the tangent. You understand, joining A 14, 0 and B 35, 350 is 350 minus 0 divided by 35 minus 14, which is approximately equal to 16.7. And this line is in fact called a tangent to the curve, precisely the tangent to the curve at this point P. We will see the definition of an actual tangent based on the notion of derivatives. So we can now say that the rate at which the population is increasing or was increasing on date 23 itself is 16.7 flies per day. That is the instantaneous rate of change or rate of increase of the population, which corresponds to that instantaneous speed of the rock at the 1 second mark. So the fruit fly population was increasing at the rate of 16.7 flies per day on day 23. Now, based on these two examples, one of the falling rock and one is this population growth of Drosophilus, we will similarly now we know how to approach instantaneous rates from average rates. Previously also I discussed about this, that instantaneous rate is something towards which average rates are approaching, and the shorter your interval is over which you are calculating the average rate of the rate of change of the dependent variable with respect to the independent variable, the closer the average rate value is towards that instantaneous rate value. So all the average rates are approximations getting better and better to the instantaneous rate value. So with this understanding, in the next calculus video we are going to see the actual notion of a limit. But I end the video here itself, and the next video is this coming Friday. So we have seen group theory, today we have done calculus. So on Friday let's go back to field theory. So that will be all for tonight. So see you on Friday with field theory. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.